Now, we are going to give a few important results. Some important results on distributions of functions of several variables. The first one, let me start with the continuous type random variable. Let x comma y be a two dimensional continuous type random variables with joint probability density function is given or is known. The first result, suppose I make a random variable x as x plus y, we can find the distribution of z directly, that is the probability density function of z is going to be integration from minus infinity to infinity the joint probability density function of x comma y by replacing x by x, whereas y by z minus x. So, this is going to be the probability density function of z when z is x plus y and x and y are two dimensional continuous type random variable with the joint probability density function small f. The second result, suppose I have another random variable u, that is nothing but the difference of two random variables x comma y, then the probability density function of u as a function of u, that is going to be integration from minus infinity to infinity the joint probability density function of x comma y by replacing x by u plus y and keep the other variable y as it is, integration with respect to y. This is for the difference of two random variables. By knowing the joint probability density function of x and y, you can directly get the probability density function of u. Similarly, the third result, that is the v is a new random variable, that is product of two random variables. You can get the probability density function of v by integrating the joint probability density function by substituting x as it is, u by v divided by x multiplied by 1 divided by absolute of x dx. This will give the probability density function of v. Similarly, the last result, the random variable w is defined as x divided by y, then you can get the probability density function of w by the similar manner. X absolute of x dx. You see, in all these four examples, we started with the two dimensional continuous type random variable and we define one random variable z or u or v or w. You can get the probability density function of z or u or v or w by using the previous theorem which I explained. The only difference is to apply the theorem you need a n dimensional random variable of transformation into another n dimensional random variable. I have explained the theorem with only 2-dimensional random variable. The same concept can be extended to n-dimensional random variable. So, here we started with the 2-dimensional random variable. We are finding the probability density function of a random variable z. You can apply the previous theorem by introducing one dummy random variable. Dummy means you can create any random variable along with z is x plus y such a way that both the assumptions are satisfied and the Jacobian is non-zero. Then find the joint probability density function of z with that dummy random variable. After that, from the joint probability density function you can always able to get the probability density function of any one random variable. Using that concept you can get the probability density function of z. That means we are applying the theorem by suitable inclusion of one dummy random variable, getting the joint distribution, then getting the marginal distribution from the joint distribution. So, that is what this result says. The probability density function of z is integration minus infinity to infinity the joint probability density function of x comma y by replacing x by x and replacing y by z minus x. One more remark over these results. I have not made the assumption of these random variables are independent or not. If these random variables are independent random variables, then you can replace the right hand side joint probability density function by product of probability density functions. Even though I have given the results for in general, if the random variables are mutually independent random variables, you can replace the joint probability density function by product of probability density functions. So, these 4 results you can remember and you can use it whenever you want to go for finding the sum or difference or multiplication or division of 2 random variables.